So let's have a look at RL circuits. We've seen a little bit of this first. We've got our voltage as usual. We have a switch somewhere when it gets thrown. We have a resistance. We have a coil. We all know that we're going to get a build-up of EMF in here when the current tries to build. So curves look something like this. We have the current slow to build up. That's our current versus time graph. It builds up to a point where it's like the inductor's not there. So as it slowly gets to that point, and you can see di dt, so if we go back to our formula, L di dt, sorry, di dt is coming closer and closer to zero. So the back voltage, when this virtually reaches zero, will be zero. And the only thing in the circuit we're going to essentially have is the voltage and the resistance. So the current will be V divided by R. That's what it's approaching. Now, that graph, we also have a voltage time graph. Now, this is voltage time for the inductor. So the inductor starts off with a maximum voltage and then drops down to zero. So that's that graph there. And the voltage it starts off with to oppose is the whatever voltage this is. So it starts off at that. And we said that this is our closing the circuit diagrams. Closing the circuit. Now opening the circuit, we get diagrams that look like this. So I said to you, the only diagram you needed to remember for capacitors and inductors was this one, for the capacitor being a voltage to time graph, and knowing that the inductor would be the other way around. So you can just memorize them that way. And we're remembering percentages. These are 30%, 37% type graphs, and these are 63%. What I mean by that is, that's how the time constant works on these type of graphs. So if you're trying to find out the voltage at any particular time, or the current at any particular time, you're going to use something called the time constant. And the time constant for these graphs, I won't prove it, you need to use a differential equation to prove it, is equal to L over R. So once you've got the henries and you've got the resistance, you figure out the time constant. And with a time constant here, we know that the current will be 63% of its maximum after one time constant. Now remember what you had to do with the 63% was actually 1 minus 0.37, right? So if you want to know after two time constants, you've got to go 1 minus 0.37 squared. Three time constants, 1 minus 0.37 cubed. With these type of graphs, if you want to know the voltage after one time constant, then it's just 0.37%. If you want to know after two time constants, it's 0.37%, or 0.37, sorry, squared, cubed, and same for these guys. Now, if this is a current time graph, and this is a voltage time graph for these guys, what are the voltages and what are the currents? Well, the current's going to start off at its maximum, right? What you're doing is you're basically, when you discharge the circuit, so this is open circuit, these four. When you open the circuit, what you're going to actually get is you've no longer got the battery supplied. Alright, so normally the way we do that is it's kind of like, that's gone. We've closed the circuit, short-circuited it, and what you're going to get is the current's going to collapse quickly. The current was flowing from positive to minus, was flowing that way, right? So this time, when you open the circuit, that means there's no connection, but you've sort of short-circuited it. It's open. It's going to try and make the current continue to flow in the direction it was, which is like that. So it now produces a voltage that way. And that voltage will be the same as what it was before, V, but then it will drop down quite quickly. As the current drops down, the voltage is going to drop down, because that voltage again is being produced by Faraday's law, which is that one when we put it in its inductor form. So these graphs work in a similar way to the way the capacitor ones do. Understanding what happens with the circuit when it charges up and discharges is important. One thing that we need to think about with these ones, though, is this guy here. When you discharge it, when you open the circuit, that is, you've got this whole thing the way it was here, but this time, so you've got your plus, you've got your minus, it's all connected up, you got your lamp, you got your coil, and it's all connected, and then suddenly just open up. Now, in this case, it's not discharging just through the same resistance. It's an infinite, well, not an infinite, but a very high resistance. And so you actually don't just get the same voltage that you started with. You can get a much higher voltage, all right? Because when the resistance is really high, the time constant is short. When the time constant is short, the IDT is short. When that's short, you get a high voltage. So we'll go into that in another video. If that stuff got you, don't worry about it. You can have a look at the video on why you get a high voltage when you open the circuit in that way. But if you basically understood the other stuff, that's good.